Good morning, everyone. Welcome to the second seminar of this month. We have the pleasure to host Dr. Jae Yun, who graduated in 2015 from SPREE. And since then, he worked as a postdoc fellow here at SPREE, focusing on characterization and understanding of perovskites. He did his master degree at UNSW in material science and engineering, and also he graduated from his undergrad studies from Yonsei University in Korea in 2008. I'm a good friend of Jae, and we have collaborated a lot. He's going to inform us and teach us a bit about his very capable technique of scanning probe microscopy. He has done a lot of good work and innovative work in understanding of the role of grain boundaries in perovskites and understanding the degradation mechanism in perovskites, and also other thin film materials and also silicon. So please join me to welcome Jae, and let's see what he has got for us.
Thank you, Amir. Thanks for kind introduction, Amir. So today, my presentation topic, so my seminar topic would be scanning probe microscope. So as many would probably know, I'm a ACAP fellow, and I would like to talk about imaging of nanoscale, in nanoscale of the charge transport layers, charge transport properties of your solar cell surfaces. So I give you a bit of contents. So first, I give you a brief introduction to scanning probe microscopy. So some of you may never heard about this before or have some experience, but I just give a brief introduction about atomic force microscopy and Kelvin probe force microscopy that I mostly use, and how do we actually obtain contact potential differences and how that can be actually related to your device performances. And I will also talk about surface photovoltaic, which can tell you about charge transport properties in nanoscale. Then I will have some FAQ sessions, so we can discuss about how we can actually measure your solar cell properties in nanoscale. So the motivation of this work, actually I started my PhD here in 2010, and some of you probably know or may seem this as completely new, but when I joined a PhD here, I started working on crystalline silicon thin filament glass, so it's called CSG technology. So if you can see the structure, it's very similar to what we do in wafer. So we have a silicon nitride as a passivation layer, and we form a silicon with different dopings, and then we crystallize your thin film, so they around 2 to 10 microns thick. At the time, we try different methodologies to crystallize your thin film, because you could form a lot of defects in your material because of the large thermal coefficient differences between your silicon film and your glass substrate. So at the time, I was doing a laser crystallization. So we scan a continuous wave diode laser across your sample surface. And as you can see, you form a grain structure along your scanning direction of your laser. But you also form a large amount of defects in your material. So I was studying the effects of defects, saying what sort of defects do we have? And so if you take a look at this EBSD image, you can see that there are twin boundaries, sigma 3 twin boundaries existing along these scan direction. So understanding the material characteristic of these defects were very helpful, but I still wanted to know what would be the exact properties, like open circuit voltage, charge transport properties, photocurrent properties of these these defects. In order to see such small defects, small scale defects, I gotta come up with something that has a spatial resolution of few tens of nanometers. So that's sort of motivation to use this AFM technique, which can give you up to Armstrong to few nanometer scale spatial resolutions. So atomic force microscopy, I just give a quick introduction. So it was invented in 1986 at IBM Research Center. So it's I think many of you have used this before or familiar. It just measures the interaction between your top surface of your tip, top atomic atoms of the tip with your sample surface. So it's basically works on the changes of your spring constants between your sample and the tip. So those atomic interactions can be monitored, and depending on your tip size, say tip radius, you can get into, that actually determines your resolution of your image. So in AFM, there are different modes, and I usually use non-contact mode because later on I will explain about Kelvin probe force microscopy, which uses a non-contact mode AFM. So in non-contact mode, we have spacing between tip and your sample in about a few nanometers. So they are constantly interacting, and what we do is we actually going to vibrate your tip at slightly above the resonant frequency. So your tip's going to vibrate on top of your sample. So once there's a interaction between your tip and sample, for instance, attractive or repulsive force, you rise a shift to your resonance frequency. So and also that change is actually going to be monitored by a laser reflection here. So the laser will be constantly following your tip, and the changes in oscillation will be monitored, and the feedback signal is applied to keep the constant force between your tip and sample, so you can constantly measure your sample surface. So changes amplitude is monitored usually, and that's sometimes we call that amplitude modulated non-contact mode AFM. So we use similar analogy for measuring the electrical property of your sample, and I will go more into detail about Kelvin probe force microscopy. What we do is we measure firstly atomic force interaction. So you actually measure your height profile, and once that's being measured, we're going to lift slightly up of your probe, of your tip. Then we are actually going to measure the capacitance interaction between your tip and sample. So the Kelvin probe force microscopy, we use two pass modes. First pass, we measure the height, and second mode, we are going to measure the contact potential differences. So let me talk about briefly on contact potential differences. In contact potential differences, we basically measure a work function of your sample. So what we measure is that we have a sample tip with a known work function. We usually use like metal, gold, silver. We can use platinum, diamond, those kind of AFM tips with a known work function. And a sample surface, we don't know what work function is, but once your sample and the tip are in close interaction, you actually form a tunneling through these two surfaces. So for instance, you have a work function higher than sample surface, and that actually establish a potential between your sample and the tip. And that potential actually allow a current to flow between your tip and the sample. And this is actually an equation that how we actually determine the work function of your sample. So if you know your sample work function here, tip work function here, we can always know, we can measure the differences between, and you can calculate your work function of your sample. So we always use in order to get contact potential differences, we actually apply a DC bias that is equivalent to your potential differences. So we nullify the changes in this circuit, and that's how we actually obtain your contact potential differences using the Kelvin probe force microscopy. So actually, I think measuring contact potential differences or measuring work function of your sample is quite, I would say, quite straightforward. You can always obtain this kind of information when you use Kelvin probe force microscopy with your tip and known work function. If you see this image here, you can see that we can always get topography image. So this is a surface of a CGTS sample, and you can get topography image. You can see that the grains have like 5 to say 700-800 nanometers, and we also can get contact potential difference mapping once the topography has been measured. So actually they measure at the same time. So there's one scan of a topography mapping, then we scan contact potential differences. So if you see this image, so what I like to show is the sample has been passivated with alumina, and after passivation, if you compare these two images, we can clearly see their contact potential difference is very different. So for instance, you can see that before the passivation, you can see that topography and CPD maps are quite similar. So you can see the features, some features are actually following the topography, but this does not mean that we have a effect of measuring surface height. We're actually measuring the contact potential signal of your sample. So that is actually confirmed by your CPD image of your same sample, but it's being passivated. So once it's being passivated, you can see that you don't actually see similar topography image compared to this one. So it actually clearly shows that you can actually get your changes of your surface potential, which is tuned by, for instance, chemistry of your surface, impurities, or something that influence the electrical property of your sample surface. So if we can always get, sorry, I don't know why it's been slightly jammed, I think. You can see that we can always get a nice curve of distribution of your work function of your sample. For instance, this one is the passivated one, and this is original one. Sorry, this is passivated curve, and this is your reference sample. You can see that there is a shift of your median work function. And what does this tell you is that you can see that it's got actually the broadness of your work function has been reduced, which means that you sort of have a very uniform work function over your surface. So which is confirmed by this image here. And we can also see that work function has shifted. That could be probably due to some other effects. And this is why we always need to, it's always good to have other sort of measurement technique results, such as, so if you see this is a TEM image which shows the existence of what elements are existing at the top surface. And in this paper, which was done with Gina, and we found that there is a lot of hydrogen contents on the top surface. Actually, such chemistry obviously changes your surface potential, and that's what we try to observe using your contact potential difference mapping. So there are many things that changes surface, shifts the work function, such as charge carrier density, surface states. There may be some local band gap fluctuations, and you may have a surface dipole, and you could also have changes in crystal orientations. For instance, your work function can be always change it, because if you have a crystal orientation with different atomic spacing, your potential to extract electron from your certain orientation can be always different. So all these things actually matters, going to matter your contact potential differences, and it's always good to have some other techniques to, to combine with and try to explain what's actually happening on your sample surface. So something we could also do is we can always try to apply bias to your tip or your sample. So this is one of the examples that I've applied for a Halide perovskite sample. So if you can see, this is exactly same sample structure as what we use in the device, but we don't have a whole transport layer and contacting metal contacts. But we can always use the same metal contacts such as gold on top of your for your probe. So what we do is we actually going to apply bias on the tip, and while it's measuring the surface height. So once you apply bias and you scan across your sample surface, and if there is any mobile charged ions that can actually move because of this bias, we expect that, for instance, we have a negative bias on the tip, and you might likely induce your positive ions to the top. And after that, right after that, we can measure the changes in surface potential. So once they are sort of aligned, we can measure what has been changed. Is your potential being changed due to the movement of ions? So those things can be done. And what I try to explain in here is that if we apply certain bias and then we keep measure your changes in potential, you can see that in a time scale of few minutes, several minutes, that your potential actually rises up, then decreases, and try to go back to its original position. In Halide perovskite, many assumes that there are mobile ionic defects that moves within several minutes, and that's how I sort of thought that this effect is actually relevant to ion migration. So there are actually many papers showing movement of iodide vacancies here. So that's sort of a tool actually to define your movement of ions. So how do I know that actually the ions have been moved? We can always apply different techniques, such as we can apply certain bias on the tip. And when you measure your height, what I observed is that you can see that after applying -7, and this is before we apply, and after we apply, what we measure is a sort of, you can see that grain boundaries have a lower height in this case. But after apply certain bias to your tip, actually grain boundaries has been sort of inflated. So actually this gave me a hint that the ions actually moving through the grain boundaries. So what I've measured is using the same technique, but measure the contact potential differences of sample surface of Halide perovskite with grain. You can clearly see that grain boundaries, as we subsequently apply biases, you can see that shift of your work function is very dominant at the grain boundaries. So it's when we apply bias, you can see that grain boundaries was originally has a lower potential, but subsequent applying this bias, you can see that the grain boundary now has a higher potential. So the work function has been changed due to the ion migration. And in this case, same analogy for the negative bias, and I could calculate changes in potential between grain and grain boundaries and show that the grain boundaries act as channels for ion migration. So these kind of things are sort of very useful when you have ions that are migrating in your sample, so that can be detected. Also, I studied degradation in Halide perovskite. I think many of you know now that there's actually a problem in Halide perovskite which has a high efficiency, but its stability is low. And I tried to study that using Kelvin probe force microscopy. So in this study, we used a FA-PBI3, which is quite stable at elevated temperature and low humidity. So they are stable in terms of having a perovskite phase. But when it goes to the room temperature or high humidity, you can see that. So this is sample image. I think it was around 40% relative humidity. If you see that after the day passes, you can see that the color changes. So, and you can see that your PL peak at around 820, which is around the band gap of the FA-PBI3, keep decreases. And we also observed a different peaks at XRD as well. We can see that there's a sort of yellow phases, different non-perovskite phases forming as time passes. And I like to study how such degradation happens in nanoscale. So that was my motivation, and I brought these same sample and tried to measure what's happening at your contact potential differences, your work function of your sample. So if you can see this image, so this is fresh image. You can see grains are quite distinctive. So you can see that grain boundaries has a slightly lower potentials. But as film degrades, grains are starting to merge. You can see from this height topography image, and you can see the potentials of these grains are actually sort of keep merging. And I also found that there's a huge gap, potential differences happening at this surrounding of this merged grain. So with the XRD results and PL results, I try to understand what's happening actually in degradation process in nanoscale. So I propose a mechanism based on what I measured previously. So moistures actually try to go through to the grain boundaries. So the grain boundary area actually acts as a channel for moisture penetration. So then it forms a non-perovskite phase of your surrounding of your grain boundaries, and then you sort of that non-perovskite phase is sort of spreads laterally, and they finally form a complete non-perovskite phase. So this is sort of advantage of using this nanoscale technique to see how that happens, how the microstructure actually affects your degradation processes. So I try to explain that using different contact potential differences at the grain boundaries and the time, and depending on the humidity levels. So this is not my work, but there are many things actually we can do, such as if we can combine with EBSD, and if we take the same spot to the AFM, we can try to correlate different surface potential for your different crystal orientation as well. So you can see that they try to correlate your samples work function with orientation. And if you also have, for instance, same material, different carrier concentration, different doping densities, you can try to correlate with the carrier densities. So there are many things actually you can try if you try to combine with different techniques. So now I like to go deeper into charge transport properties. So before, all the measurement was done in dark, so you know your work functions, original work functions. But now I'm going to illuminate light while measuring the contact potential differences. So for instance, when we say surface photovoltage, it's actually contact potential differences obtained from light, and that minus the contact potential difference measured in dark. What that means is that For instance, you have a N-type surfaces, N-type material that has a lot of surface traps, and your majority carrier is going to be accumulated on the top surface of your sample. That will obviously attract your holes, and you sort of deplete your surface. And so you sort of form a built-in potential from the surface to your bulk. And if you try to measure your surface potential, say your tip is here, and measure such band alignment, what's going to happen is that once we illuminate we introduce excited carriers, we are going to have a charge separation occurring from this built-in potential. So because of your charge separation, your contact potential difference will be changed. So the surface photo voltage can actually can tell you about density of photo-generated charge carriers and the density of minorly charged carriers. However, it all depends on your surface properties. Say if you have full of traps, or if you have a junction underneath your sample, if you have a very long carrier diffusion length, actually that all matters when we illuminate light. So we have to be very careful when we explain your results. So for instance, here, in perovskite, we have a strong built-in potential formed at this context. Say you have a transport layer and your observer layer. And depending on your transport layer, and there's a strong built-in potential at this interface, there are actually lots of recombination happening that many talks about that this is actually most limiting factor for perovskites. So if we have a strong built-in potential here, and for instance, if we don't have much traps on the top surface that made a band bending, if we illuminate different intensity of light, say, or wavelengths, say if we illuminate blue light, we would see a dominant effect from these interfaces. So depending on if you, for instance, illuminate longer wavelengths that penetrate all the way through your sample, you may have an effect of the interface and your entire layer and top surface as well. So depending on your sample properties, you need to be careful about what to look at. So you can design such experiment, say different wavelengths, different intensities, and so on. So for instance, in Halide perovskite, we can always choose different transport layer type. For instance, we can deposit a P-type nickel oxide layer underneath your perovskite, and you can also have a titania, which is N-type. And obviously, we have we have to use different TCO to balance the work function, the Fermi level of your device. So we can bring these devices and try to measure the work function. So as can be seen from these two CPD images, what I tried is, firstly, I measure potential in dark, then turn on light, dark, and light. And for the case for P-type material, P-type transport layer, you can see that when there's a light on, your potential decreases. Whereas if you see the case for N-type compact titania, you can see that your potential actually increases. So I expected that this is actually arising from what sort of carriers are accumulated at the top surface and change the surface properties. So all these properties should be considered when you measure. So for instance, I have also measured I brought the same sample structure that is used in the device, and I tried to measure the changes in contact potential differences along with the light intensities. So you can see that this is a device voltage versus intensity, and this is changes in contact potential differences versus light intensity. You can see that they follow a sublinear behavior of which between these two measurements. So I realized that we are actually measuring the charge carriers at the top surface that's being separated by the titanium and perovskite interfaces. So such method can be used actually to determine what sort of carriers, what sort of dynamics or charge carrier transport properties are we are looking at. So based on that, I tried to map and see nanoscale properties as well. You can see that grains are around 500 to a micron, and you can see in the dark they initially have a lower contact potential differences, and when there's a light illuminated, you can see that potential is actually has increased. And this is image of a grain and grain boundaries. You can see I have selected 3 grain boundaries. So this is what we measure in dark. It initially has a lower potential compared to your grain interior. As we increase the light intensity, you can see that the potential increases gradually along with your light intensity, and it has around 20-30 millivolt higher potential at the grain boundaries. So according to previous explanation, I explained that the potential differences that has risen up at the grain boundary is actually responsible from charge carriers, higher charge carriers being separated at the point at the grain boundaries. So such explanation can be made based on different assumptions with different results. And we can also do photocurrent mapping, which measures the currents of your sample surface. So it actually can measure up to picoampere scale of your current. And not the same way as the KPFM, which has a slight gap between your tip and samples. To measure your current, your tip has to be directly contacting your surface. And you sort of form your circuit here, and your current can be directly measured. And we can always introduce light. And you can see I have applied different biases to the sample. And once we illuminate light, I found that there's a more photocurrents forming at the surrounding of your grain boundaries. So you can see if I do a profile of these grains here, you can see that there is a photocurrents that is higher compared to the grain interior. And you can see that these profile actually don't follow the height profile. So for instance, if your electrical signal is following directly same as your height signal, you could speculate that this height actually affects your signals. But many of the cases, if you are careful enough, you can actually differentiate between this topography and your electrical property artifacts. So this is one of the cases I talk about the higher charge separation and charge collection at the grain boundaries. And there are actually many other techniques that actually explain such properties at the grain boundaries in Halide perovskite. But yeah, I won't go much details into this here. So I was fortunate enough to work with colleagues who can fabricate very high efficiency cells. For instance, we had a postdoc in perovskite group who put a rubidium, so inorganic cations, on your perovskites, and he can improve your efficiencies, and also the stability has greatly improved. So he asked me what would be the effect of incorporating rubidium, and I say I can probably look at what sort of nanostructures have been formed by the incorporation of the rubidium. And it was very interesting to see in perovskite without any inorganic cations, you see a potential in dark, you see such of like grain shapes with some lower potential at the grain boundaries. But if you incorporate your inorganic cations such as cesium or rubidium, you sort of form a nanoclusters. So they are around few hundred tens of nanometers, and you can see that they have sort of a lower potential formed in between the grains. And what I observed is that I illuminate light, and these darker nanodomains actually became brighter compared to the other regions. And you can see that the same thing happened for the rubidium. You can see that this originally has a lower potential, has has improved surface photovoltaic. So I explained that such formation of nanodomains actually have a higher charge separations, which could have improved your open circuit potential in your device. So I also have looked at the effect of long chain cations, say PEA, incorporate into your mixed halide perovskites, and you can see upon putting this some amount of PEA, you can actually improve your stability a lot, as well as your voltage. So if you can see device voltage here, you can see that we sort of increase the VOC as we put more and more of the long chain cations. So we have also done TEM. You can see that this is a reference sample, and this is what we see when we put 4.5% more of PEA, and you can see the grain boundaries size of the grain has been reduced by around half. You can see actually there are sort of two stacks of the grains, and people usually could expect that such microstructure of your grain, for instance, if you think that your electrons sort of can transport through the grains through your layer thickness vertically, that's actually can be beneficial for your charge transport. So, but so such stacks of grains, if you think of your grain boundaries being a defective region, non-radiative recombination region, you might expect that there are many defects, and you likely lose your open circuit potential from these defects. However, as the grain size decreases, actually you actually seem to improve your voltage in your device. And I've measured potential differences in dark and light. And if you see this image actually here, so this is potential image between dark and grain boundary and grain interior measured in dark and light. You can actually see that surface photovoltage at the grain boundary is actually correlated with your device voltage. So when you have a higher percent of PA, you see a large charge separation at the grain boundaries. So in this paper, we try to explain that probably the grain boundaries, size of the grain, may not have very detrimental effect. Rather, they may have some other effects, such as we may see a larger band gap at the grain boundaries, or even facilitates higher charge separation at the grain boundaries. We did also nice work on CGTS. This has been published in EES recently. Shin, one of the Gina's students, has made a very nice CGTS with passivated aluminum oxide, and that has don't have the cadmium. So she replaced a zinc tin oxide as a buffer layer, and she could improve the efficiency by having this aluminum oxide layer, and using different techniques, they found that there's a sodium containing copper depleted oxides are formed on top of your surface. So it's been actually shown by the TEM that several nanometer thick layer is formed on the top surface of your sample that actually passivate your surfaces. So I also tried different different wavelengths and different intensity on these two samples. So this is reference sample and this is passivated sample. In the dark, I would say the features are quite similar, that grain boundary has slightly lower potential. But when we illuminate 400 nanometer laser, when we measure the CPD, and we gradually increase the intensity of your laser, you can see that if you compare with 400 of your reference and passivated one, at certain intensity, you actually see changes in surface potential for the passivated sample, whereas this one don't show any changes in the surface potential. So this can be due to the response or absorption of your carriers due to the improved surface states. So there's removed of surface states and charge carriers being sort of easily accumulate at the top surface. So it's more responsive at this wavelength, at this intensity than this reference sample. And we can see same analogy here at 750 nanometers, which can penetrate deeper. You can see a huge changes in CPD as we steadily increase the light intensity, whereas your reference sample don't show much differences. So such things, depending on your sample, depending on your surface, we can try different techniques to identify effect of your charge accumulation on the top surface. So this is another work I'm currently doing. In Halide Perovskite, we have actually halide segregation. So we could have a different halide, specific halide segregated on specific grains, and that actually changes the band gap of your material. So if we sort of illuminate different wavelengths, for instance, if we have a iodide rich grain, which has a band gap around 1.5, and we can suspect there is a bromide rich grain, which has a band gap around 1.78. If we sort of try to differentiate these grains, we can always illuminate different wavelengths, and you can see that which grain is actually responsive to this illumination. So we can always look at band gap homogeneity in your sample surface. So this is something that I really wanted to do in the future. We can prepare a cross-sectional, we can prepare a nice cross-section using FIB, or sometimes you can just clip it nicely, and we can approach your probe to here, and we can always illuminate light, make it short circuit, open circuit. We can always apply different biases on your device. So while doing that, we can measure the changes in surface potential. So that contact potential differences will actually react based on what we apply here. So this can actually tell you the quality of your PN junction, your charge transport properties at each interfaces, and what sort of band alignments are existing across your sample device. So that's something we could do as well. So this is a summary of my seminar here. So my motivation was to look at a nanoscale structure of your material, and we can try to obtain a functional properties, electrical properties, and I usually look at differences in work functions, ion migration, charge transport, surface photovoltaic, and PN junction properties. There are actually many more we can do, like capacitance microscopy. We can also do a transient Kelvin probe and photocurrent mapping, which will be very useful to study carrier dynamics. So many of would question, where is the AFM? Because we have AFMs in the EM unit, and there are many AFMs in, actually I think there are 4 or 5 AFMs in EM unit, but to measure your surface potential, to measure your electrical properties in detail, you have to have a specific functioned AFM. So in School of Material Science, Professor Halide, who I collaborate, and I use his lab. There are lots of like 4 different types of AFM, which with a different AFMs. We can try different things, like we can always control humidity, and we can apply temperatures, we can apply forces, we actually have a tunable lasers, and sometimes you can even measure your potentials in liquid. So those things are all available in his lab. And in SPREE, we will have a AFM. So it's not going to have such a lot of function as we do in School of Material Science, but this AFM can do sort of general stuff, such as you can measure contact potential differences. I will also bring on LEDs. You can study the photovoltaic. You can map the photovoltaic. We can also do a conductive AFM, and we can always obtain IV curve on a local structures. You can try electroforce microscopy, piezo response force microscopy. You can do also phase imaging. So all this can be possible with this AFM. So this is to be installed quite soon. So sometime in a few weeks, this will be installed in SPREE. So I encourage everyone who are interested in this, please come and talk to me. We can arrange a measurement together. So I usually get lots of questions when they bring me samples. And first thing I want to say is, please provide me as much as information you can about your sample. So sometimes I get just samples without any information. So at least IV, EQEs, what have you done? So those things are really needed to actually, for me to design different experiments. So how long does it take? It's not like SEM or PL, where you just illuminate light and get your images in a few seconds. It's because your tip has to travel all your surface by step. Depending on what resolution you want, I usually do like 4 or 5 minutes of measurements for 5 by 5 micron. Difficulties, some would say, can you measure like straight away? Can we get these high resolution images? Unfortunately, it's very hard to obtain images with a high resolution with a correct electrical properties, because your sample surface can have differences in electrical properties that can change many things in your tip oscillations. So depending on your sample's stiffness, like sample hardness, you have to carefully choose your tip. So spring constants is to be determined based on your hardness of your sample surface. And shape of your tip is also important. And depending on what you want to look at, you can have a very sharp tip, but you have to remember, if it's too sharp, say if your material is too soft, it's going to poke your sample. So then it's going to, damage your sample surface. You wouldn't be getting any good information out of it. So that's something we need to consider about before we do the measurement. So what type of probe to use really depends on what your material is. So because it measures it moves with your surface roughness. So if you have a very high bump, which is in nanoscale, I've heard that if you use a black silicon, which has a very sharp needles on top surface, that is very challenging to measure using AFM. So those things has to be considered. So I would say if your roughness is around 5-10 microns, I don't think we can measure good signal out of the AFM. So yeah, anything you have, please come and talk to me, and we can always discuss. So lastly, I'd like to acknowledge firstly ACAP supporting for my fellowship on this work, and we as I told you before, we have purchased a new AFM, and these people have contributed for the purchase. I really appreciate that, and I always appreciate for the support from SPREE and people from SPREE. And also thanks to my collaborators in UNSWs and other places. Thanks for listening my seminar. Thank you.
Thanks, Jae, for your nice presentation. We have 5 minutes for questions. Please, if anyone has any questions. Yeah, Udo, please.
I have one on sample preparation. So when you do these cross-section measurements, can you just snap a sample, or do you polish it, or do you use ion milling or something to get the nice cross-section?
For instance, it also depends on if your sample is going to be damaged or changed because of the ion milling. You may think about that as well, but it's best to have a very flat surface. So first thing I would do is I would do ion milling of the cross section and measure it.
Okay. Thanks again, Jae.
Thank you.